All right, now we're recording. So, okay, so we left off. We were talking about floating point numbers, and we had our kind of our mini float, which we are using 8 bits versus the normal 64. With the 8 bits, we have 1 for the sign, 3 for the exponent, 4 for the mantissa. Okay, and we said, you know, if the exponents are all 1s and we got 0s in the mantissa, then that's going to be infinity. And we said the largest non-infinity would be 0, 1, 1, 0, because if we had 1, 1, 1, it would be infinity. And 1, 1, 1, 1. Okay, and so this becomes, this is 6, and we apply our bias of 3. So the actual value is 6 minus 3. So we have our exponent is 2 to the 3rd. Okay. Meanwhile, this part will correspond to 1.1111 times 2 to the 3rd. Okay. And so this is going to be 1 and plus a half plus a quarter plus an eighth plus a 16th, and that becomes 1 and 15/16 times 8 to become 15.5. This is the largest value we can represent with our mini float before infinity. Anything bigger than this will become infinity. So if I said, what is 2 times 8? Using our mini float, it will say it's infinity, right? Just like when I said, what's 2 to the 1023 plus 2 to the 1023 in R, R returned and said that's infinity, okay? It's obviously not infinity, but that's what the system returns. Just likewise, if we ask, what is 2 times 8, the system would return infinity, because it's not able to keep track of numbers bigger than 15.5. I guess another way of doing this, instead of all of these fractions, my students in office hours came and pointed this out, is because it's 2 to the 3, we could just move the decimal place over 3 spaces, and I have 111.1. This becomes 8 plus 4 plus 2 plus 1, 15. And this is 1/2, so we have 15.5 that way as well. Okay. Okay, so we have all of this. This is the largest value that we could represent, and what would then be the smallest value that we could represent this way? Okay. So what would actually happen? So what if I have 0 and 0, 0, 0, 0, 0, 0, 0? Okay, so this is going to be a positive number. This is 0, and so with our bias of 3, the actual is going to be -3. And then here, this translates to 1.0000, okay? And so according to our rules, we have 1 times 2 to the -3. And so that's going to be 1 over 8. And here we have 0.125. Now this feels weird because when we look at this, kind of in our hearts, we feel like this should be the number 0. Right? It shouldn't be 1/8. It shouldn't be 0.125. Something says like, hey, you know, we probably should have this be 0, right? Should be 0. Okay. And so this would be how we represent 0 in floating point, okay? And we have a new set of rules for what happens when the exponents are all 0, okay? So if the exponent is all 0, we have what's called a denormalized number, okay? So when the exponent bits are all 0, we have a different set of rules. Okay, and this is and these are called denormalized numbers. So a denormalized number is basically, with scientific notation, we always have a number other than 0 in front of the decimal or binary point. With a denormalized number, we allow, basically, the leading digit here is going to be a 0, okay? So when the exponent bits are all 0, the leading digit here is going to be a 0. Okay? The denormalized number. So when exponent bits are all 0, then the leading digit is now a 0. Leading digit in front of the binary point is 0. And the exponent part here, the exponent is going to be equal to 2 raised to the 1 minus a bias. So our exponent is going to be 2 to the negative 2, right? So so when we have 0, 0, 1 in the exponent, our exponent portion is 2 to the negative 2. And then even when we have 0, 0, 0, the exponent is still 2 to the negative 2, but what has changed is that this leading digit is now a 0 rather than a 1. Okay, so it's just, let me just kind of show you. So if I have 0, 0, 0, 1, and then 0, 0, 0, 0, here, this would be, this would correspond to 2 to the negative 2. This is following the regular old rules, and times basically 1.0000. Okay, so here I would get 1/4. And then over here, when I have 0 and then 0, 0, 0, this part is still 2 to the negative 2, except now I'm going to have 1, 1, 1, 1, or something a little bit smaller. This would be kind of like 1/4, and then what's the next smallest number behind this? It would be this, and this would be times, and now instead of a leading digit of 0, we have 0.1111 here. Am I losing you guys? Is this okay? All right, and so this becomes equal to 1/4 times 15/16, and I'm not good enough at math to figure this out. 15/64, which is 1/64 less than 1/4. So 1/4 is 16/64, right? So going down kind of at the next thing, we would have 15/64. That would be the next smallest number, or the next number there. So when you switch to 0, 0, 0, okay, basically the exponent is the same as having 0, 0, 1, except the rule shift now is we are dealing with denormalized numbers, so that the leading digit is no longer a 1 in front of the binary point, but it's now a 0. Is that okay? All right, so with that in mind, let me get... so with that in mind, we've got 0 and then 0, 0, 0, 0, 0, 0, 0. This would become a positive number. This is 2 to the negative 2 times 0.0000, which is going to be 0. Okay, and so the smallest non-zero number is 0, 0, 0, 0, 0, 0, 0, 1. Okay, and so this is going to be a positive number times 2 to the negative 2 times basically 1/16. Okay, and so here I got 1/4 times 1/16, 1/64. So this is the smallest non-zero value that we can represent using mini float. Huh? Smallest, yes, sorry, smallest positive non-zero value. So it will be denormalized if they're all zeros here. Sorry, was there a question over there though? That was my question. Yeah, the smallest positive non-zero value. Yeah, here we would technically have two representations of 0. We have positive 0 and negative 0 because the sign bit can flip. But pretty much, yeah, when I talk about smallest and largest, I'm talking about just kind of the positive side, because everything that applies to the positive side is also true for the negative side, because all we do is we just flip the sign bit. Okay. All right, so this is the smallest positive non-zero value, okay? And then if, what would be the next smallest? The next smallest would be 0, 0, 0, 0, 0, 0, 1, 0. That's the next smallest value. So I have 2 to the negative 2 times 1/8. And so this is going to be 1/4 times 1/8. And I have 1/32nd, or basically 2/64. Okay, so we're basically counting in 64ths up to this point. So this is, yeah, as far as the mini floats go, the smallest increments that we have are 64ths, right? So and then the next value would be 0, 0, 0, 0, 0, 0, 1, 1, and that's going to be 2 to the negative 2, and what is this, 3/16, and it becomes 3/64. Okay, so we're basically counting by 64ths. Okay, so far I hope this is okay. All right, let's continue on counting. All right. All right, so let's get to our largest denormalized value. Is going to be 0, 0, 0, 0, 1, 1, 1, 1, and I think we've already done this. This is 2 to the negative 2. This is going to be 15/16. Okay, and so this becomes 15/64. All right, and so So we have that, okay? And then the next value is going to become 0, 0, 0, 1, 0, 0, 0, 0. So I have 2 to the negative 2. And now that it's normalized, it's going to be 1.000. And we get basically 1/4, which is the equivalent to 16/64. Sorry. So I'm just counting using all the bits in our mini float, but the illustration here, okay, and then if we go to our next value, we'll have 0, 0, 0, 1, 0, 0, 0, 1, okay, so we have 2 to the negative 2 times 1.0001, which is 1/4 times 1 and 1/16. Okay, and so all right, so 1/4 times 17/16 or 17/64. So we're still counting by 64ths. Okay. If I continue on, and I know this is getting tedious here, but we got 0, 0, 1, and then I go 1, 1, 1, 1. Here I have 2 to the negative 2 times 1.1111. So I have 1/4 times 1 and 15/16, so 31/16. And I have 31/64. This is where I am at this point. Okay. So what will the next value be? It'll be 1/2, right? 32 out of 64. And let's just see how that gets represented in our system. Okay, so continuing counting this way, I would go 0, and then instead of 0, 0, 1, I would have 0, 1, 0, 0, 0, 0, 0. So this is 2. So just keep in mind this is 2, and we have a bias of 3, so our actual value is going to be -1. So this is 2 to the negative 1 times 1.0000, and we have 1/2 times 1, so we have 1/2. And this is 32/64. Okay. What will the next number be equivalent to? So if I increment the next value, okay, the next value in our system would be 0100001, okay? Is this going to be 33/64, or what will it be? It will be, the next increment is no longer in 64ths. This whole time we've been counting by 64ths, but now that we've gotten to this point, we lose the ability to count by 64ths. So now we're going to be counting by 30 seconds, okay? Because of our finite number of bits. So here, this thing is still 2 to the negative 1, and here I've got 1.0001, which is 1 and 1/16, or so I've got 1/2 times 1 and 1/16, or 1/2 times 17/16, and so this is going to be 17/30 seconds, or 34/64, okay? So there's no way to represent the value 33/64. Okay, if you tried to represent 33/64, the computer that has some rule will either choose 17/30 seconds or 32/64. Okay, if you choose something in between, I think it does around based on like an even rounding. So like on, if the digit before it is like a, you know, it basically it will choose which one to go up to or down to, okay? So there's no way to represent 33 64ths, okay? At least with our mini floating point, okay? And you know, maybe you're heartbroken about that, but that's just a very real thing. It's a consequence of having a finite number of bits to try to represent an infinite number of values, okay? We just don't have that ability. And the design of the floating point is that when the numbers are small, you have small increments. So when our numbers were small, we could increment by 64ths. As these numbers get bigger, as we cross over 1/2, then the amount we can increment grows as well. So now we're incrementing by 30 seconds. As the numbers get larger, so then we start representing whole numbers, then the amount we can increment will get larger as well to basically 16ths, and so on and so forth, okay? So with this one, the largest value will be 1, 1, 1, 1, which is going to be 1/2 times 1 and 15 16ths, or 31 16ths, and so we get 31 30 seconds. This is going to be the next thing, and then the next largest value is going to be 0, 0, 1, 1 times this is what is this, 2 to the 0 times 1, and we get 1, okay? And then and if I increment this, then it will increment the next value. If I write it up here, the next value will be 0 and 0, 1, 1, 0, 0, 0, 1, which is going to be 1 and 1/16. Okay, so as the numbers increase, the step size introduced, but as we increment our bits, the gaps get larger and larger. Okay, so our number line, if I were to illustrate our number line, sorry. Okay, so just imagine we've got it's symmetric, so I'm going to just start over here at 0. Okay, basically the numbers we can increment are very small until we get to what did I say? Until we get to about 1/2. Okay, and at 1/2 our step size gets bigger until we get to 1, and then it gets even bigger. And then and at 2 they get larger, right? So we get, you know, we're at 1/64ths, and then at a certain point we cross over to 1/32, and then we're at 1/16 in terms of increments, and then we'll have increments of 1/8, so on and so forth. And as the numbers get bigger, the step sizes get larger. And so when you're towards the end of the the counting range, okay, so when we're at something like 0, 1, 1, 0, this is kind of our largest range. What is our step size at this point? So this has a value of 6. So with the bias, this is 2 to the 3rd times 1.0000. So this is equal to 8. And then what's the next value that we would have? 0, 1, 1, 0, 0, 0, 0, 1. It would be 2 to the 3rd times 1 and 1/16, and so we would have 8.5. So when we get to the 8, we're incrementing by halves. Okay, so there's no ability to represent any value between 8 and 8.5. They're going to be just, the system will choose one or the other. Okay, so if it's closer to 8, it will choose 8. If it's closer to 8.5, it'll choose 8.5, and so on and so forth. Okay, and so this is effectively what's going on when we do some kind of math. If we did math using our mini float, and I said, what is something like what is, because we could represent 7, no problems, right? We can also represent 1 1/4. Right? So both of these numbers have representations in our mini float system. This would be, I don't know what this is, but it's something, okay? And then this has another representation, except when we combine these, okay, now we're going to get a value of 8.25, which doesn't have a representation anymore, okay? Now we have to store this somehow, and so the system is going to go and say, maybe it'll store it as 8, or it will store it as 8.5 or something like that, okay? And then you ask, and then later on you come down and you say, like, okay, what is 8.25? And based on the rules, it might round up or round down or something, okay? And so so if we ask, is 7.7 plus 1.25, is that equal to basically 8? This actually might be the case here, okay, using our mini float system. All right, and so these are just kind of things to watch out for, because you might have two numbers that have representations in a floating point system, but when you do an operator to combine those two, you might lose the ability to represent that number, because now you're at a kind of at a higher, because this is at like a higher order of magnitude than the other number. Okay, all to say, you know, the rules of math fall apart in floating point arithmetic, and we have to be careful. Okay, so this covers basically what I wanted to say about floating point math. And you know, again, the actual system, the IEEE 754 system uses 64 bits, and so we will have 1 sign bit, 11 for the exponent, and 50. Or am I counting this wrong? Yeah, 52 for the mantissa. Okay, and so this allows us to, you know, represent a bunch of numbers. It's the same kind of system, except you're dealing with, you know, much bigger or much smaller scale. But the same mentality of near 0, you can increment by very small amounts. As you get farther away from 0, the amount you increment will grow until you get to, you know, larger numbers. Yes? Does the denormalization rule still apply? Yes. So with the same rules, the normalized and the denormalized rules apply in the same way here, okay? Everything I did with the mini float, it follows these rules almost exactly the same. It's just I only have 3 exponent bits and 4 mantissa bits. Okay, but everything else exactly the same. Okay, are there any questions before I move on? Yes?
For the exponent, can you go over again how you got to the 3rd power?
2 to the 3rd. So right here we have the exponents are stored in the biased scheme, okay? So that means you say how many unique values can I represent with 3 bits? There's 8 unique values, okay? And then, and basically we want half of those bits to be positive and then the other half to be negative and 0. And so in that case, we say, okay, half of 8 is 4, and then we subtract 1 from that, and we get a bias of 3. So our bias, when we have 3 bits, our bias is 3, and then we say, okay, well 110 in binary is 6, and then we subtract the bias, and we get 3. Okay? We can't go to 111 because 111 is technically going to be infinity, or not a number. So our range for the biased exponents go from -3 to +3. Okay, I'm going to now introduce the topic of numeric methods. Okay, so numeric methods is basically trying to solve math equations without normal math, all right? So numeric methods is basically using a computer to kind of brute force. That's not really the right term, but it's kind of using a systematic approach to get an approximate answer without doing any kind of analytics. Okay, so we use a computer to get an approximate answer to kind of a mathematical problem. So, contrast this to, in algebra, if I said you have x squared minus 4x plus 8 is equal to 0, and I say solve I don't know. What would we say? Solve for x, okay? What would we have to do? Okay, you could use a quadratic, but I would say, complete the square, right? Okay, so we have x minus 2 squared, which if we did that would be x minus 4x plus 4. Okay, so we have this, and then we have plus 4 is equal to 0, right? And then, did I do this right? Huh? I don't. Maybe I messed something up, right? Now I'm embarrassed. Like I'm nervous now. Okay, so we got x minus 2 squared is equal to negative 4. Oh, now we're we have problems, right? Because now we have imaginary numbers and stuff. So okay, this was a bad example. All right. Okay. All right. Okay. So now we all right. So let's say all right. Let's say I used a better example, but you would solve basically. You use the tools you've learned in algebra. I should have known this was not going to work. Okay, but anyway, I'm embarrassed now. Let's do minus 8, and so this will be plus 4, and now it's what, minus 12? Minus 12, right? Yeah. When you complete the square, you've got to subtract 12 to counteract this, and so now we have x minus 2 squared is 12. Okay. All right. So now we can solve this out, right? And so we got x minus 2 is equal to the square root of 12, and then we have x is equal to 2 plus or minus root 12. Okay. And I guess you would have gotten that with the quadratic equation. Which basically does this. Okay. But let's say you didn't remember the quadratic equation. You didn't know how to do this. All right. Which, and I almost got in trouble here. Well, we could do some numeric methods instead, right? So that's with algebra. Basically, with the numeric methods, we do something along the lines of, and there's basically better approaches, but one would be for root finding. You have several approaches, and one is just kind of like, let's plug in a value for x, and see what that equals. And based on what we get, maybe we say, okay, let's change our value because we didn't get 0. So we're going to either increase that or decrease that, pick another value, and we're going to just keep going through some kind of process until we get a value that's pretty close to solving our thing. So, basically, root finding would be something along the lines of plug in a value for x. Okay, and then see what you get. Okay, alter your guess, and then keep trying until you get something close to 0. Until basically f of x is pretty close to 0. So I'm sorry, if I said f of x is this thing and we want to find where f of x is equal to 0, this is what we would do with algebra. And then with numeric methods is you basically just plug in some value into f of x, you see what you get, you alter that based on, and these are what the different algorithms are. You've got different algorithms that say this is how you should alter your value of your guess, and then we alter it based on that. We keep trying until we get f of x equal to 0, right? So we're going to start here, and then once we have some numeric methods down, we can do some applications of this. All right, so the first method is called fixed point method. Okay, so you have f of x, right? You have f of x, and you want to find x so that f of x is equal to 0. Okay. Well, what we're going to do is we're going to alter f of x so that we can solve a different problem, okay? So we will alter f of x. We will alter f of x, okay? Something kind of like, we will alter f of x. We now have g of x. Okay? G of x is basically going to be, it's not necessarily this, okay? But g of x, we'll say, could be f of x plus x, okay? So we could say, so one situation, it could be that g of x is equal to f of x plus x, and we will use fixed point iterations, okay? To solve for g of x equal to x, okay? So if we find a solution for g of x equal to x, then that will be where f of x is equal to 0. Oh wait, did I mess this up? F of x, g of x. Do I wait? f of x minus x. Oh gosh, I'm confusing myself here. Okay, so we're going to use fixed point iteration to solve for g of x equal to x, and then basically the solution to this will also be a solution to the other, okay? And the solution to g of x equal to x will be a solution for f of x equal to 0. Right? Log of x, yeah, okay. Okay, so why would we bother doing this? Okay, well, it turns out that for some equations, if you plug in a value for if you take your current value of x and then you plug it into g of x, it will give you a new value, and then you plug that in. And so here, let me just write out the algorithm, because my explanation with words is terrible. Okay. Okay, so you have, we'll say x of n. This is our current guess for x. All right, and then we calculate g of xn, okay? And then we use that as our next guess for our next guess for x. So this will be, so we have x at time n plus 1 is equal to g of xn. Okay, and this is the entire algorithm, fixed point iteration algorithm. Huh? No, it's just plug in your current guess into the thing. Whatever it spits out, plug that in again. And how is this supposed to work? Well, basically, whatever the function is, this will, depending on the function, it could converge to a point where what you plug in here gets closer and closer to the next value, until a point where the thing you get here is this thing, and then it has converged. So let me just kind of give you an example. Let's say I have we want to solve, oh, is it 250? All right. Okay, we will have to pick this up on Monday. Okay, all right. We'll end here, and then we'll pick this up next week, and continue on with our numeric methods. All right. Have fun. I hope to see you guys at the Hadley Wickham seminar, and have a good rest of the week and weekend.